For the first time in human history, a spacecraft has dared to enter the sun's atmosphere. This incredible achievement by the Parker Solar Probe will be remembered forever, as no metal or even the toughest planet in our solar system can survive such intense heat. This raises a fascinating question. Why doesn't the Parker Solar Probe melt in this extreme heat? How is it functioning so efficiently at temperatures not of thousands, but millions of degrees? Back in the early 1900s, scientists noticed something very strange during their study of the sun. They were estimating the sun's temperature based on the light's wavelength and color using a spectrograph from Earth. Just so you know, the color and wavelength of light are directly connected to its temperature, but the results that appeared before the scientists gave rise to a mystery that still puzzles experts today. What they observed was that while the sun's surface had a temperature of around 5,500 degrees Celsius, the outermost atmospheric layer, known as the corona, was far hotter, over 500,000 degrees Celsius. This means the corona is at least 100 times hotter than the surface. It's as strange as feeling more heat when moving away from a fire rather than toward it. This strange phenomenon has baffled scientists for over a century. The corona is usually hidden in sunlight and is visible only during a solar eclipse or with the help of special instruments like a coronagraph. After NASA was founded in 1958, many space missions were launched, one after another, venturing into space. But to understand this corona mystery, it was necessary to send a probe directly into this superheated region and observe what's really happening there. However, this was no easy task. The sun's environment is so intensely hot that even imagining it is difficult. Iron, for example, melts at 1,500 degrees Celsius, and even tungsten, the toughest metal on Earth, melts at 3,422 degrees Celsius. Both would be destroyed in seconds on the sun's surface. Now imagine what would happen in the corona, where the temperature is several times higher. There was another major challenge, reaching close to the sun itself. The sun's gravitational pull is so strong that it binds all the planets together in their orbits. Let's first understand that if we want to bring a satellite back from Earth's orbit, its speed must be decreased so Earth's gravity can pull it back. On the other hand, if we want to send it to another planet, its speed is increased to escape Earth's gravity. For example, when sending a spacecraft to Mars, it's first placed into Earth's orbit using a rocket, and then at the right moment, angle, and speed, it is propelled out of that orbit. Getting a spacecraft out of Earth's orbit requires a massive amount of energy. Rockets help it reach orbit, but to send it further, smaller onboard rockets are used. The sun, being 150 million kilometers away from Earth, requires a much larger angle and an even greater amount of energy to reach. No rocket exists yet that can provide that much power. So NASA experts came up with a clever solution. Before sending the Parker probe to the sun, they would send it to Venus. Venus, being the second planet from the sun, was used to increase the Parker probe's speed using gravitational assist. But there was a catch. Venus is smaller than Earth, meaning its gravitational pull is weaker. That's why the probe had to orbit Venus 24 times to gain enough speed and reach close enough to the sun. On August 12, 2018, Parker Solar Probe was launched from Cape Canaveral Air Force Station. NASA planned this mission to last 8 years. Over this period, it would use Venus 24 times to gradually spiral closer to the sun. In each orbit, Parker gets about 37 hours to study the sun. So, over 8 years, the probe will complete about 900 hours of scientific observation. On April 28, 2021, NASA officially confirmed that Parker probe had successfully entered the sun's corona. The mystery that the corona is hundreds of times hotter than the sun's surface was once again confirmed. But why is it like this? What force is mysteriously heating the corona to such extreme levels? Research is still ongoing. Now let's return to our original question. Why hasn't the Parker probe melted despite being so close to the sun? The part of the spacecraft facing the sun is covered with a special heat shield made of carbon foam. But this is no ordinary foam. It's specially designed by Ultramet Company to handle the sun's heat. This foam is 97% hollow inside, making it extremely efficient at insulation. On top of this, a carbon-carbon composite layer has been applied, made by mixing graphite and resin. This layer was applied to both sides of the shield and then superheated, turning it into ultra-pure carbon, which is known for excellent heat resistance. To add another layer of protection, the side facing the sun was coated with white ceramic paint to reflect most of the sunlight before it can be absorbed. Not just that, the rest of the spacecraft has been designed in such a way that it always remains in the shadow of this heat shield. Even so, Parker Solar Probe can only withstand up to 2,500 degrees Celsius, while the corona's temperature is over 500,000 degrees Celsius. So how is it surviving this environment? According to the laws of thermodynamics, heat transfer needs a medium. On Earth, we feel heat because air molecules transfer it. But in space, especially near the corona, the particle density is extremely low. So even if the temperature is high, there's nothing to transfer the heat effectively. Think of it this way. Putting your hand in boiling water burns immediately because water molecules touch your skin. But if you quickly put your hand in an oven at 300 degrees Celsius and take it out, you may not even feel it. That's because in the oven, there are fewer molecules to transfer heat. Similarly, in the corona, The heat exists, but the lack of particles prevents efficient heat transfer. Experts say the surface temperature of Parker's heat shield reaches around 1,200 degrees Celsius, while the side facing away from the sun remains below freezing. That's because there's no matter in space to carry heat from one side to the other, and this is exactly why the Parker Solar Probe hasn't melted, even this close to the sun. We hope you enjoyed this amazing video from Black Hole Facts. Please like and share if you found it interesting. Thank you once again for your wonderful comments. See you in our next mind-blowing episode.